So hello everyone. So welcome to our channel 361 Physics. Today we are going to talk about some diagrammatic questions which are very essential and important for the upcoming SLC examination 2018. Okay, so let us begin the discussion from the very first question. So in the beginning, two questions are just kept in the model of 5 marks type of problem. So later on I have just kept some diagrammatic questions, and uh, let me just begin the discussion of this first question. So this is here. So what do you mean by buoyant force? So buoyant force is quite simple to understand. If you have some kind of fluid, and if you place some kind of object in fluid, it is always not necessary that there should be water. Sometimes it might be some kind of fluid as well. Okay, so until and unless you place the object, the buoyant force doesn't come in play. But as soon as you place the object in this fluid exerts a kind of force in upward direction. Okay, so the region of this buoyant force is initially up to this level there was a fluid, but this object likely to displace this amount of fluid from here. So as a reaction, this liquid will push the object in upward direction. Okay, so this kind of force is called a buoyant force. That means simply if the object is placed in fluid, then the fluid exert a kind of force that is called buoyant force. And buoyant force always come in play when the object is placed inside the liquid. Otherwise, no buoyant force will be shown by the fluid. Okay, so fluid might be liquid or air. Air also follows the basic principles, basic ideas, basic guidelines of the fluid. Air is also a kind of fluid. So is it necessary for a body to have a lower density than the fluid to float on? It's not always necessary, because there are two things. Suppose if it is your container, liquid container, and if you have an object designed in such a way that if it can displace liquid equal to its own weight, then okay, weight of the object will be equal to weight of liquid displaced, no matter what the density of this object be. Okay, or no matter what the density of the material of which this object is made up of. It doesn't make any sense. Okay, it doesn't require. So if this object dimension is organized in such a way that it can displace liquid equal to its own weight, then the object can flow. This is one situation. The another very important situation in here is the uh, the idea of the surface tension. Suppose this is your fluid, and if you wish to keep a needle whose density is fairly greater than water, like your if you just have a pin like this one. Let me just use another color so that you can recognize it well. So suppose this is your needle, and the density of this needle is obviously it is made up of iron and steel, and the density is in the order of this. Okay, but liquid is the density is in the order of 1, but it still can float in here. So the reason behind this one is the surface tension. So there could be two possible ways to float the object in the fluid, even if the density of the object is greater than that of the fluid. Okay, so अब्जेक्टले आफ्नो वेट बराबरको लिक्विड डिस्प्लेस गर्यो, या द अब्जेक्ट चाहिँ कुनै तरिकाले सर्फेस टेन्सनको हेल्प लिएर बस्न सक्छ भने so not necessary that they should have a lower density to float on. Okay, the third one, what volume of helium if a balloon is to lift a weight of 100 kg including the empty mass of the balloon? Okay, so here is some mass. This is a certain amount of mass there. This mass is to be lifted by this helium. Okay, helium has fairly lower density than that of the air. That's why what volume of helium is necessary to float this mass of 108 kg, and even while lifting this empty balloon has to be lifted by oneself. So here is a simple mathematical calculation, well, just from the principle of uh, of this floating. Okay, to float the object in fluid, we know the force, that is upward force given by the buoyant force. Okay, so this buoyant force in upward direction and the weight force in downward direction, they should be canceling one each other. Okay, or should be equal to one each other. If situation is achieved, then the object will be floating. So let me just write, this is the buoyant force, and this buoyant force should be uh, equalized by the weight. Okay, so the buoyant force is very well known. So buoyant force or of thrust is given by v rho z. Okay, and the weight is given by simply mass times acceleration due to gravity. And in here, this is the density of, okay, air, because air is going to be uh, displaced, right? Okay, now another is, this is v rho of air g will be equal to here mass, the total mass of this empty balloon, as well as some mass kept in here. So see, even the helium present in here has to be lifted. Okay, this is the helium has to be lifted there. That's why we have to consider this helium as well. For that reason, I will be taking the total mass of the object, and this is going to be density of helium times density, sorry, volume of helium plus 180 kg. Okay, so own mass also has to be lifted by this buoyant force. Okay, so now let us put the values and we can easily calculate the magnitude of V. So the total volume of the helium that has to be lifted is simply this G will be cancel out, and we can simply uh, divide this 180 by this and this. Okay, so density of air, density of air is in the order of 1.29, and the density of helium, okay, density of helium is in the order of 1.8. Okay, sorry, 0.8. Okay, 1.29 minus 0.179. So if you just do this simple mathematical calculation, so you are gonna get simply 160 meter cube. And so okay, so this is the calculation for this question. So यस्तो खालको question अरूमा पनि अरू situation लिएर पनि सोध्न सकिन्छ. That's why you should be very careful about the calculation of this kind of question. Okay, so now let us move on to the second question. This question is related to, again, the fluid dynamics. So this is a very natural question related to the human body. So state the principle of continuity. So you are well known about this. The total volume of the fluid flowing through any section of the canal is going to be constant. Okay, so the rate of flow of fluid is always constant, no matter what the size and shape of the fluid containing device be. For example, say this is a large area and this is a small area. So, but there is no difference of the amount of volume of liquid crossing through this section or this section, and this will be well determined by the area, and in other word, we can say the volume. So this is area A2, so here velocity will be V2, and area A1, this is velocity A1. So these are going to be equal. That's why it is going to be conserved. The total volume of the liquid passing through any canal is always conserved. No loss, no gain. Okay, per unit time, the amount of fluid flowing through a canal per unit time is going to be constant. That is what the principle of continuity. In hydropower project station, the orifice of the tunnel carrying water is made extremely small just before the turbine fan. Okay, this is so simple. So suppose this is your reservoir, and from this reservoir a big tunnel is brought, and when you just reach the power station, so it's just near the power station, the orifice, that means opening, is made extremely small. See, the reason behind that one is, see, the principle of continuity. The area in here is high, and here the velocity is relatively low. But if you make this area to be extremely small, the velocity is going to be extremely high in here. And if you just put on the turbine fan over here, to just generate electricity, connecting this generator through a belt. Then see, this water will hit the fan with a great force. That's why this turbine will rotate very quickly, and the amount of generation of the electricity is going to be higher enough. For that reason, to increase the velocity, to increase the force in here, over the turbine fan, the orifice of the opening of this tunnel tube in very close proximity of this turbine fan will be made extremely small. Okay, this is what the region for this one. So again, here the continuity principle comes in play. Okay, let us move on to the numerical in here. So this is a very pragmatic question related to our human body. So in human body, the oxygenated blood flows from the aorta. This is very well known to everyone, and the radius is generally in the order of 1.2 centimeter, and to the capillaries of the uh, radius of this at a respective speed of 40 centimeter. So in here, let me just show you with the follow. This is your aorta. So in aorta, the blood will flow in the order of 40 centimeter, and all these will come to these capillaries. Very extremely large number of capillaries are there in our body, which are responsible for the exchange of gas. Okay, so the oxygenated blood lasts up to capillaries, and even the deoxygenated blood will be started to collect from the capillaries, and finally it comes to the vena cava, and finally it gets inside the uh, heart. Okay, fine. This is the general biology. Okay, let me just come back to my own discussion. Here again, we have to calculate the number of capillaries. Okay, so it's quite simple. So again, we have to use the uh, principle of this continuity, because no matter what amount of blood is coming from in here, all the blood will be conserved, even if there is a millions and billions of capillaries inside the body. That's why we have to use the principle of continuity. So by using principle of continuity, let me say the area of the aorta is A1 and the velocity there is V1. Okay, so all this blood is going to be passing through the capillaries with velocity v2. Okay, let me just write the velocity v2, and the area of individual capillaries is a2. But you know, well, the aorta is here 1. That's why the total blood flowing through the aorta is 1 times this much. But this same blood is going to reach the different part of the body with a very large number of capillaries. That's why I just like to put this in. So now you can easily do this mathematical calculation. So the radius of this is 1.2. So 1.2 into 10 power minus, okay, minus 2 into uh, pi with the square here. The area is pi r square, into velocity here is 40 centimeter per second. Okay, 40 by 100 meter per second. Okay, so this is what your uh, velocity in here. So area is going to be like your 0.4 millimeter. That is 4 into 10 power minus 3 square into pi into velocity is here like your 5 into 10 power minus 4 meter into the number. So just you have a single variable which you can calculate. So I have calculated it for this one. So this value is roughly in the order of this is power 4, this is power to 6, and here to power 10. If you just divide it by 1, in I believe it comes in the order of million. No, not billion. 10 to the power 9 is billion. So its value I have just mentioned here, its value is in the order of 7 into 10 to the power 9. Such a huge number of capillaries will be taking part to flow the blood through our body. So following the principle of this uh, continuity. Okay. So now let me move on to another problem. So this is also related to fluid statics. Okay. So here water and the oil are poured in a U-shaped open-ended tube and allowed to come into equilibrium. Find the density of oil. Okay, so this is a very interesting type of problem. You have to remember one very important concept about the fluid is no matter what shape of this container might be. So suppose this is the container, such a irregular container is there, and I believe if you just try to calculate the density in this region. Pressure in here, pressure in here, pressure in here, pressure in here, everywhere the pressure is going to be same in fluid statics. Okay, so the exactly same principle is going to be utilized to carry this particular problem. So you can see there the location of A and location of B uh, are just in a same horizon. That means the pressure at here A and the pressure at here B is going to be equal. Okay, so these are the open-ended five. They are at contact with atmospheric pressure. That's why we have to take in consideration about this atmospheric pressure P naught as well. And the pressure in here is due to P naught plus liquid, that is this is oil, and another is this is P naught plus the amount of water in here. So utilizing these two pressures, we can easily calculate the magnitude of the density. Okay, so pressure at A and pressure at A and pressure at B when the liquid is in stationary condition, static state, the pressure in the given horizon is always constant. So this is P naught plus H rho oil into G plus, oh sorry, so this is going to be equal to P naught plus H rho water into G. So this P naught and P naught will be cancelled out as they are equal, and later on it left with this G, and this G will be cancelled out. Okay, so you just can find the value of this oil. Height of the oil is, this is 27.2. So let me just write 27.2 into 10 power minus 2 into density of oil equals to this height. We don't know, but we can calculate from here. This is 27.2 minus the height of this water is only this much. So this is 8.62 whole into 10 power minus 2. This is in centimeter. That's why I have done this one. And the density of water in CGS system is going to be equal to 1. So if you just calculate this density of oil, so I believe it comes on definitely lesser than 1 because the oil is floating in here. Okay, so the density of oil is in the order of 4 point. Okay, I have kept all the parameter in here in SI system. That's why I have to put here 1000 so that it comes in the order of 680 kg per meter cube. So this is what the answer for this one. Now let us move on to another problem related to this, again fluid dynamics. Again, it is related to a human body. A very practical and pragmatic question is mentioned there. So you can just see a patient is given to a blood transfusion. It is very always necessary in the medical treatment. The blood is flow in the tube, which is raised to the bottle and a needle and inserted inside the vein. The internal diameter is 25 millimeter of this uh, mm, this one needle. The internal diameter of 25 millimeter long needle is okay. The length of the needle is 25 millimeter, where the radius is 0.8 millimeter, and required to have a flow of blood at a 2 centimeter cube per minute. How high should the bottle be raised so that if the blood pressure is 78 torsoli above the atmospheric pressure? This is very important to understand. Say, suppose here is blood, and it should have, suppose this is a blood, and if you want to transfuse inside your body, you should remember one thing, that suppose this is your hand, the blood, suppose this is your vein. Okay, the blood pressure, the pressure of this blood has to be more, okay, more than the blood pressure in here at the uh, भेन. ओके, यहाँको प्रेसर ज्यादा भएन भने यो प्रेसरले यहाँभित्र पुश गर्न सक्दैन. द्याट्स वाइ द प्रेसर इन हियर हैज टु बी मोर in comparison to that of the pressure in here. Okay, so let me suppose this is some pressure P1 here, P2 and so on, so that there is a difference of pressure. That difference of pressure will actually let the blood to flow. But how to carry this numerical? So you know well, what amount of blood will come from this vessel? Well, the same amount of blood will be injected inside the vein. That's why we can utilize the concept of Poiseuille's law. The Poiseuille's law simply provides us the information about the amount of blood passing through the container or passing through this tunnel per unit time. That is Poiseuille's law, particularly related to the volume of liquid per unit time. Okay, so sometimes we just write V only in Poiseuille's law. Okay, volume per unit time is simply V. Okay, so I utilize this concept to carry this numerical. Let me just do this mathematical treatment. Let me just tell you uh, what is going to be here. Okay, so let me just write from Poiseuille's law, the amount of fluid flowing per unit time is going to be pi r to the power 4 p2 minus p1 whole divided by 8 eta L. Okay, so we can simply utilize this. Now P1 and P2 are known. So P2 is going to be the pressure over here. This is your what P2. Let me just write it on the color so that it would be properly visible. Okay, so this is what your P2 and this is what the pressure in here is P1. Okay, so let me just calculate now. So everything is known to us now. Okay, so I have to calculate this P2. So if I just simplify this P2 is going to be so this P1, so this P1 and this all. Okay, so P1 plus 8 eta L into V, this divided by, okay, pi r to the power 4. This is this one. So again, this pressure in here is all due to this blood. That is density of blood, that is h rho z. H means height, density of blood because blood is flowing, and the acceleration due to gravity. Okay, so this is p1 plus 8 pi 8 eta lv. V means volume of blood per unit time, so pi r to the power 4. So if you want to calculate density, height of the blood, because density is mentioned in here. Okay, this is the height. So height can easily be calculated as 1 by density of blood into acceleration due to gravity, whole p plus all these parameters. Okay, now the very important thing is simplifying this quantity. We have to calculate v and all, and even we have to convert this torsilli into mm of hg. So torsilli means millimeter of mercury. Okay, so in the honor of name of this torsilli, who try to calculate the atmospheric pressure with using mercury and so on. Okay, let me just move on. So to calculate this height of the blood column is going to be 1 by, so what we need is the density, and that is given to us like this one. So 1.05 into 10 to the power 3. Okay, this is what the density of the blood, and the acceleration due to gravity is well known, 9.8. And now let me just keep up the parameters. 78 torselli means 78 millimeter of mercury, so we can simply write 133 newton per meter square. Okay, so in SI system we just need to bring into Pascal one. Okay, plus, so the other parameter is 8 into eta into and so and so. So 8, so eta is given to us in here. Okay, so eta equals to 4 into 10 to the power 4 into 10 to the power minus 3. Okay, into 8 eta L. Okay, L means so 25 millimeter. So this is what your 25 into 10 to the power minus 3, and volume. Okay, volume means so what we have here is okay, 2 cc per minute. Okay, 2 cc per minute means 2 into 10 to the power minus 6 divided by 60. Okay, so I have to divide all this quantity. So okay, all this quantity divided by how much? This is pi r to the power 4. Pi means pi, and r means r is here something 0.8. That is 8 into 10 to the power minus 4 square. Okay, fine. If you just do these all calculation, you can just get it in the order of 1.04 meter. Okay, so this is how we can crack this kind of numerical. So this is a very practical question, can be asked in examination. Examination pattern to questions maximum questions are daily life related questions are okay. So let me move on to another question. So I have further questions. So I already have done this question number 4. Now let me move on to this type of question. This is related to magnetic effect of current. So there are two wires. So this is in here one wire, that is current is being just coming out of the plane of this board, and another is just carrying the current in this direction. And we have to do one thing. Two wire are carrying oriented normally to each other and separated at 20 centimeter. Okay, this is your 20 centimeter and 20 ampere and 12 ampere respectively. Okay, in here 20 ampere and this 12 ampere, this is known to us. So the current in here is IA, I1, okay, I1, and this is IB, okay, I2, whatever you can say, something is written in the diagram. And we have to calculate the magnetic field in here, the midway. Okay, so if you wish to calculate the magnetic field in here, you have to be very careful about the direction of current as well. Sorry, yeah, direction of current, because if you use right hand rule, so suppose this is your suppose this is the direction of flow of current, and if you just place the thumb in this direction, so and if you just scroll your finger, if your thumb will be pointing in this direction, the finger will go inside the plane of paper, and in here the finger come out of the plane of paper. Okay, so यतापट्टि, so यता आउँछ, यो चाहिँ यता भित्र जान्छ. So यही युज गर्ने यहाँनिर यो कन्सेप्ट, यसको मतलब if the current is flowing in this direction, the magnetic field is above the current. That means the magnetic flux is coming out of the plane of paper. Okay, now the current is in out of the plane of paper. If you just put your finger towards you, and if you just scroll your finger, then you find that your finger will be curling at this location. Your finger will be curling in this direction. Okay, so यो दायाँतिर आउँछ, यो फिङ्गरलाई आफूतिर राख्ने थम्बलाई, अनि फिङ्गरलाई यसरी कर्ल गर्ने यो डाइरेक्सनमा है. इफ यु जस्ट लुक एट योर फिङ्गर्स इन कर्ल डाइरेक्सन, so your finger will come in this direction. So there are two directions, that's why we have to get the resultant of these two. So this is what you're gonna be the resultant one. So what you can do is, and obviously these are at 90 degree, there is no problem to just do mathematics, the angle will be 90. So for example, suppose this is your current magnetic field 2, and this is magnetic field 1. So this is your total magnetic field. This total magnetic field is going to be how much? Under root of B1 square plus B2 square into plus 2 B1 B2 cos 90. So cos 90 is going to be 0. That's why we don't have to do any kind of mathematical treatment for this one. So you just need to get B1 and B2. And you know well, so the magnitude of B1 is the straight conductor. Straight conductor हो यो पनि straight conductor. Straight conductor को magnetic field निकाल्न एकदमै easy छ. So magnetic field, no matter B1 and B2, this is mu naught I by 2 pi distance. R means this location. R पनि भन्छौं, D पनि भन्छौं, A पनि भन्छौं, no matter. Okay, this is A. So this one, यसको लागि अब यो एउटा हो हैन, यो एउटा हो, त्यसको लागि let me just write I1, त्यसपछि फेरि mu naught I2 plus 2 pi A. ओके, अब यो ए चाहिँ कति राख्ने? ए भनेको यहाँबाट हेर्दा पनि 5 सेन्टिमिटर, सरी 10 सेन्टिमिटर, यताबाट हेर्यो भने पनि यो 10 सेन्टिमिटर. That's why the magnitude will be like this one. So you can simply put these values. So I forgot one thing, just to calculate this one, we have to put here one this and square and this square. Okay, so this is how we can easily calculate. So I haven't calculated the value for this one, just to save the time, because the video is going to be longer. Okay, let me just erase and move on to another. Okay, I believe you got the idea of this problem. So this is very important. एकदमै बुझ्नु, अन्डरस्ट्यान्डिङ कुन क्वेसन एकदमै हो, यसले सोधिन्छ यस्तो खालको क्वेसन, एकदम विचार गरौँ. अब यो भन्दा अझै इम्पोर्टेन्ट क्वेसन अर्को छ. है। सो यो एउटा दिएको छ, द सर्कुलर कन्डक्टिङ रिङ इज ओके। पहिले एउटा सर्कुलर कन्डक्टिङ रिङ थियो, यसलाई टुक्रा गरेर यता र यता जोडियो, यसरी जोड्दाखेरि यस्तो खालको भयो भने के अमाउन्ट अफ करेन्ट यतातिर पास भइरहेछ, के अमाउन्ट अफ करेन्ट यता पास भएको छ है। ओके, यदि यो कन्डक्टिङ वायर एकै खालको हुन्थ्यो, जस्तो हामीले त इन्फर्मेसन फरक फरक दिएको छ है, एकै खालको हुन्थ्यो, यहाँबाट पनि करेन्ट आई फ्लो गर्थ्यो, यहाँ पनि आई करेन्ट फ्लो गर्थ्यो, यहाँ म्याग्नेटिक फिल्ड निकाल्न कसैले लाउँदैन, त म्याग्नेटिक फिल्ड इज गोइङ टु बी जिरो। किनभने यो वायरको कारणले, यहाँबाट फ्लो भएको करेन्टले यहाँबाट फ्लो भएको कारणले म्याग्नेटिक फिल्ड आउँदैन। यु नो वेल, इफ द location of the magnetic field is to be determined is in the axis of the conductor. एक्सिस मा कहिले पनि म्याग्नेटिक फिल्ड आउँदैन, त्यसैले यो पार्टले यहाँ म्याग्नेटिक फिल्ड लिँदैन। अब यसले दिने भो, यसले दिने भो। अब विचार गरौँ, इफ यु जस्ट पुट योर थम्ब इन दिस डिरेक्सन, योतिर डिरेक्सन यो डाइरेक्सनमा राख्ने हो भने यो लोकेसनतिर तिम्रो कल अफ फिङ्गर कसरी घुमेको हुन्छ भन्दा तिम्रो यहाँबाट आएको फिङ्गरहरू यसरी यताभित्रतिर घुम्छ, भनेको यहाँबाट म्याग्नेटिक फिल्डको डाइरेक्सन के भयो, इन्टु द प्लेन अफ बोर्ड। अब यताबाट हेर्ने हो भने इफ यु जस्ट पुट योर फिङ्गर इन दिस डिरेक्सन एन्ड इफ यु जस्ट कल योर फिङ्गर, तिम्रो फिङ्गर चाहिँ अब यताबाट घुमेर यतातिर आउँछ, यो लोकेसन भनेको आउट अफ द प्लेन अफ पेपर आउँछ। करेन्ट सेम, रेडियस सेम, म्याग्नेटिक फिल्ड यहाँ के हुन्छ, सेम हुन्छ, त्यसैले जिरो हुन्छ है, करेन्ट इक्वल्ली फ्लो भएको छ भने। तर यहाँ क्वेसनमा इस्यु छ है, क्वेसनले आफै भनेको छ कि अमाउन्ट अफ करेन्ट फ्लोइङ थ्रु दिस टु पार्ट्स अफ द section or two section of this circular coil, circular portion is different. Okay, so here the magnetic field will be different. So what you simply do is यो यसले दिने magnetic field कता हुन्छ, into the plane of paper, यसले दिने magnetic field कता हुन्छ, out of the plane of paper यता, भने यो दुईटाको म्याग्नेटिक रिजल्टेन्ट म्याग्नेटिक फिल्ड के गर्नु पर्यो। सो इफ यु जस्ट से दिस इज B1 and this is B2, then if you take B1 as a positive, then B2 has to be negative. So total magnetic field is going to be B1 minus B2. So how do you get B1 and B2? Quite simple. सेमी सर्कुलर आर्कबाट कति म्याग्नेटिक फिल्ड निक्लिन्छ भनेर हामीले क्याल्कुलेसन गरिसकेका छौँ। स्ट्रेट कन्डक्टरको कति हैन, स्ट्रेट कन्डक्टरको सोलेनोइडको कति, रिङको एक्सिसमा कति, रिङको सेन्टरमा कति, सेमी सर्कुलरको कति, एभ्रिथिङ हेज बिन क्याल्कुलेटेड एन्ड यु नो द magnetic field due to semicircular coil is always mu naught I by 4r. Okay, so here I1 and here this is mu naught I2 by 4r. Okay, let me just not write this one. This is I1, so you can just subtract. Okay, you do tell a subtract gonna sakihalincha, you can easily find the value of this one. Let me move on to another. I believe you got the idea of this all. Okay, if you have any kinds of issues, then just write down there in comment section, and if you wish to get some questions from other chapter, so you can just write there in comment section. We have already prepared 9 or 10 videos related to this diagrammatic question, particularly for the examination 2080 physics SLC. Okay, so the final question in here, this is related to electromagnetic induction. So you know, this is the magnetic field going inside the plane of paper, and this is a circular loop that is just being pulled out. Okay, and you know, if you just pull made the conductor to move through this magnetic field, the EMF is going to be developed, and because of the development of the EMF, some current will flow in this loop, and because of this current flowing inside the loop, and as the loop is inside the magnetic field, some force will be felt by this loop at that time. Okay, so यसमा अब हामीलाई फोर्स नै क्याल्कुलेट गर्न लाग्छ। फोर्स क्याल्कुलेट गर्नको लागि पहिलेको यसको फिजिक्स बुझौँ है। सो तिमी यसलाई पुल आउट गर्न चाहन्छौ भने इट इज लाइक अ मोसनल इएमएफ। यो सेक्सन बाहिर जान खोज्यो भने यसले म्याग्नेटिक लाइन्स अफ फोर्सलाई काट्छ, यहाँनेरि के डेभलप हुन्छ, यहाँनेरि इएमएफ डेभलप हुन्छ। त्यो इएमएफ डेभलप भएको कारणले के हुन्छ, मानौ यतातिर हाई पोटेन्शियल, यतातिर लो पोटेन्शियल हैन, यता तान्दाखेरि नो म्याटर दिस मिन्स टेक लाइक दिस वन, करेन्ट यहाँ फ्लो हुन्छ। फेरि करेन्ट फ्लो भएको कुनै कन्डक्टर, करेन्ट फ्लो भएको करेन्ट क्यारिङ कन्डक्टर म्याग्नेटिक फिल्ड भित्रबाट हिँड्दैछ भने के हुन्छ त, that experiences a kind of force, and that is what we have to calculate in here. So you have to apply two situations in here, that is, one is motional EMF and the second is the force experienced by the loop moving inside the magnetic field. And so simple. And you know, well, if you wish to calculate the total force that is going to be BIL sine theta, and this is theta is the angle between your magnetic field and this magnetic field and the length of the conductor. So this portion is just moving and they are perpendicular to one each other. Magnetic field inside the magnetic field भित्र अनि मोसन चाहिँ यता. ओके, लेन्थको डाइरेक्सन चाहिँ यतातिर हैन. यस्तो हुन्छ भने जम्मा टोटल एंगल कति हुने भयो 90 डिग्री. So this is going to be equal to 1. So this is going to be BIL. So we have to calculate. Length is given. This is 0.350. Another is magnetic field is given. Okay, some Tesla, 0.65 Tesla. Okay, velocity is given. Okay, this velocity is maintained. So force त निकाल्यौं. त force निकाल्नको लागि हामीलाई के चाहिन्छ त करेन्ट चाहिन्छ. करेन्ट कहाँबाट आउँछ? यहाँ करेन्ट फ्लो कसले गराउँछ? यहाँ फ्लो गरेको करेन्ट भनेको यहाँनिर डेभलप भएको EMF ले दिने हो. त्यसो भए म के लेख्छु? B equals to induced EMF divided by the resistance. यहाँ केही रेसिस्टेन्स होला यो वायर हैन, रेसिस्टेन्स इन्टु लेन्थ. ओके, सो यति भयो. सो E को भ्यालु यति. E फेरि हामी के गर्न सक्छौं त? B equals to again B, E means EMF is BLV sin theta. Again sin theta is not necessary because the area vector, area sweep gareko, area vector swept out. The area vector swept out is the magnetic field is inside. Area vector swept out is just perpendicular to the plane of paper, and this is going to be 90 degrees. So BLV will be sufficient here, and divided by the resistance, EMF by resistance times L. So B square L square V by R is to be your total EMF, and particularly I have calculated this, and it is about 0.628 Newton. So this is how I concluded the discussion for this one. So follow us and stay tuned. Try to figure out more questions. Just write them in comment section. We will be facilitating you. And finally, I like to say good luck for you all. You will be able to do your best in the examination. Thank you all. Okay, so I want to sign off right now. Thank you.